Okay, now things are going to get more interesting. I promise you. Except this doesn't matter. So that was easy. Now we're going to do some more interesting operators, and things are going to get more interesting, I promise you. So, set operators, we get them, it's easy. Remember, whenever we have that is not something, that generally involves a set subtraction, with the exception of some times, but you will see what that means. Then there are even more complicated ones that are for all queries. We will see that. But of course, these are very simple queries that basically take two sets of things and then just smash them, right? You take their intersection, union, and so on. But lots of queries are going to be much more subtle than that. So that's where we get some interesting operations. So before I get more fancy, I'm going to show one operator that's going to be important in many places. It is called the rename operator. So the rename is written with a rho, R-H-O. So no operator that we will see explicitly changes the schema. The rename operator will actually change the names of attributes. So you can take, for example, suppose you have Marvel heroes. And in fact, the attributes that it had was hero ID, hero, and real name. Okay. But for whatever reason, I want to change the names of the attributes. So what you can do is you can use the rename operator. So the rename operator basically is a row with the name of the new relation. So like R1, or yeah, let's call it R1. And then you have the option of giving a new name to all of these attributes. So you can say HID1, hero 1, and real name 1. And then which relation that it applies to. In this case, it applies to Marvel heroes. Okay. This is actually one of the ugliest looking operators. So we will see different ways of doing the same thing. From my perspective, as long as I understand that you are renaming attributes, any format is fine. Another format that you can use is to do the following. So this is option 1. Option 2, which I like, that you can say, well, I'm going to create a new relation R1 you can use this kind of equal or otherwise. And of course, doesn't have to be like this. You can be even more useful for yourself. You can just call them x, y, and z. That would be so much easier to write. Okay? So both methods are fine. Whichever one you use, I'm happy. I like the second one easier, but the book will use the row. So either way, it's just basically renaming the names of attributes. Now remember that this is a logical operation. You are not taking the relation and making a physical copy of it, right? It's like you are reading it in a slightly different way. And an important thing about this is that you can take any relational algebra operation and take the results and give it a name. So this is going to be useful when we write multiple operations that combine, then you can just keep assigning them new names. So this is what we are going to use rename for. Okay? So rename is a completely cosmetic operation. It just renames the relation and the attributes. And often the relation name is not important, but the attributes are. It doesn't change the number of attributes. It just gives them new names. All right, so now let's get to something more interesting. So selection and projection are the two basic operators. Yes?
So if you have a set A, set B, and all have attributes in the take set B and you rename these attributes to X, Y, Z, can you still compare set A and set B?
No. So the question was, suppose that I had R1, XYZ is a copy of Marvel Heroes, right? So what happens if I take R1 and take union with Marvel Heroes? Like, for example, right? So what happens when I take a union like this? It is not defined. It fails, professor complains. So theoretically, this is not valid, right? So this is not defined because not the same schema. This is why we care about kind of correctness versus, what really happens in real life. There's a ton of really horrible HTML in the world, right? That is totally illegal, but actually your browser displays it fine. Yes? So the point is that it's technically not right, but in a database it may work, but logically it's not correct. Okay? So we are first trying to be pure, so you understand the logic, because this is where everything is well defined. But in real life, there are of course many ways that this is violated. So selection basically is a slice operator. So go through every tuple in the relation and select only those tuples that satisfy condition C. So all tuples in R that satisfy condition C. So two important things. When you do selection, your conditions are the same. So your schema is the same. So schema does not change. And C is a Boolean condition that operates on the attributes in relation R, right? That basically doesn't talk about anything that happens outside of R. So it's only about the attributes that are in R. Okay. So for example, and this is sigma selection, you get it? So for example, I can find all heroes who do not have an alias. And let's also find all movies made before 2010, before history. Okay, and then we'll get more fancy in a second. All right. Okay, let's do this one first. So all movies made before 2010. So I'm going to look at all the tuples in the movies relation and then select only those tuples where the year is less than 2010, right? So it's going to be something like select year less than 2010 from movies. So the result that you get is, again, the same schema as movies, except it now has a subset of the tuples, only those tuples that are made before 2010. Okay? Now let's think about all heroes who do not have an alias. Who would be an answer to this? Jessica Jones. All right, good. That's why I put her there. All right, so how do I write that? If they don't have an alias, then their real name is the same as the hero name, right? So, so I'm going to select all tuples where hero is equal to real name. From which relation? So I take the union of these two, right? Then select what I want. So I'm going to have Marvel heroes, union DC heroes. And then from this, I'm going to select name is, hero. I'm going to get used to the schema soon, equals real name. And you can have a Boolean condition that basically has multiple conditions. The schema is too simple to do that. Okay, no, this is not good. All right. All right, let's do a TV show. So let's find all TV shows who, that were on CW since 2000. Not a good query. So let's see, all heroes who. All right, so let's see. Well, it's going to be not a great query, but we will still write it. So all heroes who are in a TV show since 2013 and still in production, still being shown, still running. Thank you. All right. All right. This is not a good query because it's like we don't know how to write the whole thing. Because we don't know how to just return the heroes, we know how to return all the TV shows, right? So let's just write all TV shows for now. So all TV shows since 2013 and are still running. So you're going to say, okay, from TV shows, select first year greater than or equal to 2013 and ended is equal to no. Right? Now, right now we are not actually writing something. This is not going to be implemented. So I don't care that this is an integer, this is a string or Boolean. I'm not using string codes, right? So this is just like very hand-lazy in terms of typing because it really doesn't matter. But obviously when you implement it does. But for the part of this homework, we are not going to, for the part of relational algebra, we don't care about any of that. Okay? So now think about this. This is a very limited operation. It doesn't allow you to say anything other than what you can tell by looking at the tuple alone. Every time you take the relation, take one tuple, look at it, and what you can tell, right? Looking at a single tuple, can you tell if that hero, let's say, let's take a look at this, okay? So let's say I'm looking at this tuple, that this says that there is a show called Hero and it has hero ID 12, right? Can you tell that this hero has not been any other TV show? Just looking at that tuple alone, can you tell? Right? Because when you're looking at the tuple, you can tell the attributes of that tuple, but you cannot tell something about the state of the whole table, right? So you cannot tell that this person has not been in any other TV show. So the selection is very limited. It can only say things about the attribute stack. If you're looking at that tuple, can you tell if that hero has been in a movie? No, because this is about the TV shows, right? So this is the point that is very limited, and it can only apply to whatever those attributes are. Okay? So let's look at the second operation. It's called projection. This is even more limited because selection was a select slice operation. Projection is the dice operation. Okay? So you will basically keep some attributes and remove the rest. So it's basically all tuples in R, but only containing attributes right? So, you're not going to be able to really project attributes that are not in the relation, right? So it's only valid if A1 through AN are attributes that are in R. So for only attributes, otherwise this is not defined. Now projection is again one of the very simple but very tricky things, okay? So for example, if I had the query where I had selected some set of TV shows, I can find um, all the heroes in that by just projecting the hero name or hero column. So let's find the name of only the real name of all heroes. So find real name of all heroes. So the real name is an attribute. So take the relation, the union of both of them, and then project on real name just to find only the real name of all the heroes. If I wanted to find the ID of all the heroes, then I would have done the same. If I wanted to find ID of all heroes in a TV show, what do I do? Project the HID from TV hero. So there's already a very common, theme is that you saw how many times I had to write Marvel hero union DC hero, right? So eventually you realize that this is not a great data model because I have to keep doing this, irrelevant thing. So maybe I should actually store them together, right? I actually put them separate so I can show you some union queries that are simple enough. But technically, you shouldn't store them separately. It makes no sense. Okay. How about find all years in which a movie was made? A hero movie was made. How about this one? Find all years in which a hero movie was made.
Projection years and then.
Now, when I project year from movies, will I have the same number of tuples as the movie's relation?
Yes, because when you do the projection, you're not actually, like when you moving, you look at values, so not all the tuples.
But now the logic comes back and hold on. But where's this? All right. Right. Technically true, but we said that output is always a relation, right? So, and the relations have to be sets, right? So, this is the main trick with projection, right? The projection may actually reduce the size of the relation, right? So when we move to SQL, there's going to be a bagged version of relational algebra that doesn't remove duplicates, so that will be exactly what you said. But for this version, this is very important that since output is a set, it in fact will be only the unique values, right? So remember set semantics. Which will actually make life much more interesting because of this, right? So the projection is useful in two ways, right? It removes things that are not relevant to your query, and it also changes the schema so you can do set operations, for example, by only looking at the attributes that are relevant. Okay? So now we can do some cool stuff. Okay? So now we can find, okay, find the ID of all heroes that were both in a movie and a TV show. Okay? All right. Give yourself a minute to write this down. Find the ID of all heroes that were either in a TV show or a movie. And a movie, sorry. And a movie. Well, we will do the other one too. So, I'm going to take TV shows and I'm going to project HID. Okay? So, project HID from TV shows. I'm going to take hero in movie and project HID. Okay? So now these two things have the same schema. So I can use set operation. So I will use set intersection. Right? All right, here's one more. Find all movies with, so find the ID of all movies with no superheroes in them. Okay. There is one in my database by design that I didn't want to write the hero names. So I mean, it may or may not exist, but need to find the ID of all movies with no superheroes in them. Okay, so think about that for a minute. Sorry? Movies database. There we go. So yeah, movies, MIT movie name year. Hero in movie, you have hero ID. All right. So no superhero. So it's going to have set subtract, right? So what is the set of all movies? Which relation stores that? Movies. And I'm going to set subtract heroes. Well, the heroes doesn't tell me which hero is in which movie. Hero in movie, right? But you cannot set subtract those, right? They are told a different schema. So you only have to distill the information you need. So I can do project movie ID from movies. This is all the movie IDs of movies. Subtract from that all the movie IDs where there is a hero. Okay. So a movie is listed here if there's a hero in it, right? So if there is no movie ID in this relation, then this movie has no heroes in it. All the others I'm going to subtract, right? So this is kind of one of the tricky ways you start to get more complicated relations. This is all the movies. This is all the movies with a hero in it, right? So when you subtract one from the other, you get the result. So this is movies with heroes in it. This is all movies. Okay, so subtract from all movies the movies with heroes in it, then you get movies with no heroes in it. And this is the only way I can do it, but I cannot actually find out the names of those movies. We have to do some other thing. I leave it to you as an exercise to find which movie that is. Any questions on this one? Okay, so it turns out this is why you can do this, interesting stuff, because it removes the duplicates, right? So this is only the information that is important, only the movies that have certain information. Okay. Now this is my username. Okay, so slice, dice, and then we have only one more left. There's only one more operator, most complicated one. Okay, so in any of these operations, you always only look at a single relation at a time, right? You can take two relations, take their intersection. You cannot. You can only look at a tuple at a time or slice. But very often, all these queries that we want to write, which we don't know how yet, actually involve going through multiple relations, right? So if you wanted to find the name of movies with, let's say, Iron Man, okay? True, they are all called Iron Man, but anyway. So you basically have to now trace multiple relations. You have to first find that Iron Man is actually H2, and then you know that H2 is in M2 and M3. Then you go and find that M2 and M3, actually the names are Iron Man and Iron Man 2, right? So these kinds of queries you cannot write with any of the operators that I showed you before. Okay? Are you convinced of this? Okay? Think about it that you cannot do it. Right? Because when you do selection, you cannot select from another relation. It has to be in the same relation. It is not a set operation at all. Okay? It's something that is different. So to be able to do that, we are going to write Cartesian products first. So Cartesian product is like this. Okay. If you have seen Cartesian product in math, it's the same exact thing. It basically tells you that this is all tuples of the form Rns. So let's write it even more. All tuples of the form such that R is a tuple in S, R is a tuple in R, S is a tuple in S, and R and S has all the attributes in R and in S. Ultimately, what I'm doing is I am multiplying the tuples. Okay. So let's see it in a very simple example, something much simpler than what we have. So let's say R has two attributes, A and B, and has two tuples, A1, B1, A2, B2. And S has, let's say, C and D, and it has C1, D1, C2, D2, and C3, D3. Okay? So there are two tuples in R, three tuples in S. When I multiply them, there will be 6 tuples, right? So the new relation R times S is going to have all the attributes in R, all the attributes in S. Okay. And this only works if R and S have different attributes. So if they had the same attribute, then I cannot disambiguate between the A that's from R and A that's from S. So Cartesian product doesn't work. They have to have different schema altogether. Okay? We will see that's very important. So basically, I take each tuple of R, A1, B1, multiply it with all the tuples in S. So C1, D1, C2, D2, C3 and D3. And the same thing with A2, B2. Right. For every tuple in R, and for every tuple in S, there's a new tuple in here. Okay? Cartesian product is very, very stupid. It doesn't really make any kind of matching or anything. But the nice thing that it does is actually puts tuples in R and S side by side. So after I do this, now I can do all sorts of selections to select only those tuples that have a certain property. Right? That's the only point of doing Cartesian product, except for one we will see later, is to be able to do queries that basically build on top of this. Right? So for example, one of the most frequent things you want to do is to combine tuples, let's say the movies from one with the heroes from that movie. You can put them side by side and you can do a selection. But it's very important to understand that the Cartesian product alone does not achieve that. Okay? I'll do it the hard way and then we'll move to the easy way. So for example, I can take movies, or I can take hero in movie with a certain, let's say, Marvel heroes. When I multiply them side by side, I will have HID hero real name and HID and MID. But this is not good because you have now two HID columns. You cannot distinguish which one comes from which one. Okay? So again, to be pure for now, we are going to do a renaming. So I am going to first rename R, hero in movie to be called R, so that I have HID and MID1. So I am going to then take, let's say, Marvel heroes and do a Cartesian product with R. Okay. So now I have S. And the schema for S is it's going to be HID, name, no, hero, and real name because of Marvel heroes. And then because of R, I have HID1 and MID1. Okay. So now I put side by side all tuples, but these tuples are going to have tuples that are for different matches, right? So for example, it doesn't have any kind of selection, so this Captain America, this one tuple, is going to be multiplied by every single tuple in here. Okay? If this hurts you because you think that this is so inefficient, we'll see why that's not actually the case. But first understand what that means logically, because like, why would you do that? I understand. Okay? So you have as many tuples as there are for Captain America for this, right? But ultimately what we care is to match the hero IDs so that they are for the same hero, right? That is a very common operation. So what I'm going to do is I'm actually going to select HID is equal to HID1 from S. Okay. So now from the Cartesian product, only select the tuples where the hero IDs match, and then return project the hero. So this will be a new relation that has the hero names for heroes that are, so tell me what this is in English. So what does this compute?
All the heroes that Marvel heroes that were in the movie.
That's right. So these are all the Marvel heroes that were in a movie, right? So all hero names for Marvel heroes that are or that were in a movie. Right? It sounds a little bit like set intersection. In fact, join the Cartesian product is somewhere between set intersection and somewhere between a totally different semantic. So you could technically do something like this, but the problem is that you need to match the attributes, right? We only had HID, but I wanted to return hero, so now I can. So, so this is basically the general idea that you do Cartesian product and then you do a selection, okay? So, but this seems like really cumbersome, right? So first you rename an attribute so it's not the same, then you do a selection, and then you project it out. You didn't even care about hero ID at the end. So given this cumbersome way of doing things, there are now shortcuts to doing some of the same stuff. So in fact, often you don't write Cartesian product, but you have to learn how to write this. But you actually write things like joins. So joins are not, again, core operations because they are derived. Okay. So the most common one is called a Theta Join. So the theta join is written with a bow tie. It's a formal operation. And a C, R join S on condition C. This is just the same as do a Cartesian product first, and then select only tuples that satisfy C, which is exactly what we just did, right? So I could have written the same thing, but I could have written after I rename. So I had now from this point on, I could take R join with Marvel Heroes, such that HID1 from R is equal to HID from here. And then if you want, you can project on here. Okay? So this query and the above query are the same. So these two are exactly the same thing. Okay? This is just a shortcut. Instead of doing a Cartesian product and then a selection, this just joins them both. So joins are just for your convenience. Okay? Now that we know join, you can do even better. Wait, there's more. For 1995. So you can do a natural join. That's one you're gonna like. All right. I think the book uses star. I think the book uses star. I don't remember. So the natural join is hard to describe mathematically. So the natural join basically is an equality join on the attributes R and S have in common. So, in this data model, anytime I had heroes, that attribute was named HID. So often when I need to do join, I need to join on HID anyway, right? So I don't need to actually do this. And the nice thing about the natural join is that it's not going to have in the schema 2 copies of HID, because that's unnecessary. Okay? It's going to be an equality, and the schema will not replicate the common attribute. And if they have multiple attributes that are the same, it's going to have the same. So I could have written things like, for example, I could write, Marvel Heroes with, hero in movie, and with movies. Okay, you're going to see what I'm writing in a second. All right. Okay, so it says that to a join between Marvel heroes and heroes in movies, right? When you do this, you are matching heroes with the movies that they are in, and you are eliminating all heroes that are not in a movie, right? So it's basically you are joining and doing a selection. What you are selecting is you are eliminating movies that have no Marvel heroes, and you're eliminating heroes that have no movies. So then you're doing a join with this to only find the names of the movies that are in this set. And you have this now huge relation, right? So this relation now has the schema that has hero ID, hero, real name. Then hero in movies will give me a movie ID, but I'm not going to repeat hero ID because this is natural join. Then I'm going to join this with movie, so it's going to have movie ID again, and then movie name and year. I'm not going to repeat movie ID again twice because it's natural join. And this is going to be only for those movies that have a Marvel hero in them. So if you wanted to return their name, you can take this and you can project on movie name, for example. So what this would be is all the Marvel, all movies with a Marvel comic hero. Okay. So natural join finds matching values for the attribute in common, removes all tuples from either relation that are not matching, and doesn't replicate the common attribute. Okay? So when we come back on Monday, we will do a bunch more queries. And then we are going to start talking about normalization and functional dependencies.